Hi, I'm Carrie Laboski. I'm a professor of soil science and extension soil fertility and nutrient management specialist. Today we're going to be talking about nitrogen management. So to start off, nitrogen is our nutrient that's most often limiting crop yield in Wisconsin. Nitrogen plays an important role in plants. Specifically, it's a component of amino acids. They're the building blocks of protein. Now, there's a lot of nitrogen in our atmosphere. It contains about 78% of dinitrogen gas. However, plants can't use that nitrogen directly. Therefore, we need to get it converted somehow. And one way is biological nitrogen fixation via the symbiosis between legume crops and rhizobia, or chemical fixation through the Haber-Bosch process where we create fertilizer materials. Now, it's important to keep in mind what nitrogen deficiency symptoms look like in different crops. I just have a corn crop here as an example, but in general for all crops, nitrogen is mobile in the plant. So that means as it becomes limiting for plant growth, the plant will start cannibalizing itself. It will move nitrogen from lower in the plant up further into the newer growth or the new tissue. So you observe deficiency symptoms lower on the plant first. So in this photo, you can see the lower leaves have what we can call fired, where we see the nitrogen deficiency, and it's moving up the plant. And if we just focus on this one particular leaf, you'll be able to see how the deficiency progresses in the plant. So not only from the bottom up, but from within a particular leaf. It starts at the leaf tip and progresses up the midrib before it starts consuming the outside edge. And that's important to note that is distinctly different than potassium deficiency, which also starts at the bottom, but is from the leaf margin inward. So here it's the tip firing up the midrib. Now, as we progress further into nitrogen management, I think the absolute key to really doing well in nitrogen management is to understand the nitrogen cycle. That is truly the most important tool in our nitrogen management toolbox. And so with that, you're going to see this particular graphic a number of times as we walk through the various components of the nitrogen cycle to keep that in mind so you're aware of how the cycle works and how it impacts potential management. So if we start with the diagram, we have several inputs in the system. So we have our soil. Some of our inputs of nitrogen into the system would be from crop residues, manure, fixation, as we just talked about, from legumes, fertilizer applications. Those are all nitrogen inputs into the soil system. Our losses from the soil or removals out of the soil include leaching, denitrification, and plant uptake of nitrogen. Now you can see there's a lot of arrows going on here as we transform from one product to another, but also within there's a lot of cycling that's going on. So we're going to try to break this down and focus on some of the key pieces. So the first part we're going to talk about is soil organic matter or organic additions to the soil. So that would be manure or crop residue. So it's really focusing on the organic end in the soil. And now if we think about our Wisconsin soils, most typically have 1 to 5% organic matter. We do have mucky soils that have much greater organic matter content, and our organic soils truly, by definition, there's no mineral material, so they're 100% organic matter, but often from a practitioner standpoint, anything more than 20% organic matter is what we're considering organic soil. Now, in any given year, approximately 1 to 4% of organic matter decomposes or mineralizes annually. And that's highly dependent on weather conditions, so soil moisture and temperature. But it's also dependent on the composition of the organic matter. So organic matter are these huge, complex molecules in the soil that we haven't really fully been able to identify. They're a variety of things, and they behave differently. So you could take two soils, one from across the road from each other. They're mapped as the same soil, but they've been managed a little bit differently over time. So maybe they have fairly similar levels of organic matter, but it's possible that the mineralization of nitrogen from them is different because they've been managed differently in the past, such that the composition of the organic matter is different. And that's really important to keep in mind. So we can have these rough guides that 1 to 4% is available annually, but it does vary. It's hard to just use one particular number when you're trying to make a back of the envelope calculation, for example. Now, when we look at organic and mineralizing in the soil, we need to keep in mind the carbon to nitrogen ratio. And that's the carbon to nitrogen ratio of that material, and it influences whether additional nitrogen will be mineralized or released versus immobilized or fixed within the organic matter. So when we see a carbon to nitrogen ratio of less than 20 to 1, we can typically expect that it's going to release nitrogen. When the C to N ratio is greater than 30 to 1, it's probably going to immobilize N. Meaning that, for example, sawdust, you have a high C to N ratio, you put that in the soil. It's actually, as the bacteria are focusing on breaking down that organic material, they need nitrogen to do that, so they will outcompete a plant for that nitrogen that's in the soil. So it will immobilize or make unavailable for a plant that nitrogen. Now, when we have a C to N ratio between 20 and 30, what happens is really dependent upon the composition of that material. I have found myself in my research that with manure materials that are between 20 and 30 to 1 for C to N ratio, sometimes they'll mineralize N and sometimes they'll immobilize. And it really just depends on their composition. Now, this slide is showing you just the general C to N ratios of organic materials that exist. And you can see soil microorganisms themselves have a C to N ratio of 8, soil organic matter is about 10, alfalfa, when we start looking at that, is 12. Now we start going on the high end, look at sawdust, it's 400 to 1, grain straw 80 to 1, corn residue 61. So different crops are going to have different C to N ratios, so that factors into how quickly they break down and also how much N might be immobilized during that process. Now, back to our diagram here. So we talked about organic matter mineralization, and let's get into more details of this process here, the conversion from organic matter to ammonium. And that's called mineralization, okay? And again, it's organic N to ammonium. Soil bacteria and fungi are what control this process. They make that happen. And when we're talking about living organisms as the functional part here that are controlling that mechanism, they have to have conditions under which they like to operate. So they work best when temperature is between 75 and 95 degrees Fahrenheit. That doesn't mean they won't work outside that range. They just tend to be a little bit slower in their activity when you have cooler or very high temperatures. Now, oxygen is extremely important for mineralization to occur. It occurs much, much greater in aerobic soils than it does in anaerobic soils. And that's important to keep in mind. So if you have waterlogged soils, you're probably going to have very little mineralization occurring. And moisture content of the soil is also important. So it's related to that oxygen content, but there needs to be an adequate water available for the bacteria to work as well. And we tend to see maximum bacterial and fungal activity when we're between 50 and about 70% of the water-filled pore space. So that's our transformation from organic matter or manure or crop residues that are added to the soil, how they're mineralized and converted to ammonium. Now, when we look at ammonium here as it sits on this nitrogen cycle, there's a few ways it can get there. So it can be from organic matter mineralization, fertilizer application, you might be directly applying ammonium, and its fate has a few things. Ammonium can be taken up by the plant, as shown here by that long arrow. It can be immobilized back into organic matter, meaning that the soil bacteria and fungi will consume that nitrogen and put it back into soil organic matter. The third thing that can happen with ammonium is nitrification process. And here, this is where ammonium is transformed to nitrate. And that's a very important component. So if we look at this nitrification process, again, we see ammonium going to nitrate, and then on to nitrate. Nitrate is taken up by plants. Nitrate does not last particularly long in the soil. Now, this reaction is controlled by a number of things. First of all, you have to have ammonium in the soil. So if you don't really have very much ammonium in the soil, you're not going to get much production of nitrate. Again, temperature is extremely important on the mineralization process, and the temperature ranges are similar to that as temperature is very important for the nitrification process, and the temperature range is similar to that of the mineralization process. Soil pH is very important. If you have pHs less than, say, 4.5, maybe even less than 5, you're not going to have as much nitrification. And you could look up in some textbooks and it might suggest that 8.5 is an ideal pH for nitrification, but that doesn't mean by any means that it only occurs at pH 8.5. It occurs for the whole spectrum of where we're liming our soils for good crop production, which is going to be typically in the pH 6 to 6.8 for most of our crops. Now, oxygen is required for this. If we don't have oxygen, this process is not going to work. So that's an important component as well. So if we have an anaerobic soil, we're not going to, meaning there's no oxygen or very, very little oxygen, we're not going to get much nitrification occurring. Now, the other component of this is you need to have a population of nitrifying organisms. And any two soils collected from different fields, or even perhaps in different parts of a field, they may have different populations of nitrifying organisms. So you need to have them to make this happen. If for some reason you have a soil that has few nitrifying organisms, as far as number of organisms, but also the populations are rather small, we won't get nearly as much nitrification. Now, I wanted to show you this graph. I think it's very interesting, and it's looking at the effect of temperature, so soil temperature, on the nitrification process. In this study, ammonium sulfate was applied to a soil with about 3.4% organic matter, and it was incubated, and the amount of nitrification was measured. So what we're looking at the bottom is the percentage of ammonium applied that was nitrified. And here, just point out a few relevant temperature regimes. So these soils were incubated. They were kept at somewhere about 50% water holding capacity, if I can remember correctly, and they were subjected to different temperature regimes. So this top one is where for 24 days the temperature was held constant at 81 degrees Fahrenheit. And we could see that over that time period, 100% of the ammonium was converted to nitrate. Now, if we look at the opposite end of the temperature regimes, here we had a constant temperature of 41 Fahrenheit. And with that, over 24 days, only 29% was nitrified. So some real big differences between 41 and 81 degrees Fahrenheit. Now, typically with nitrogen management, 50 degrees is suggested as the temperature that when the soil temp gets below 50 degrees, we have very little mineralization and also nitrification occurring. But I just want to point out that even at temperatures less than 50 degrees, you can still get mineralization, or I should say nitrification occurring. Now, two other temperature regimes I'd like to point out would be this one right here. The third one down from the top, this is showing a cooling trend. This would be much like fall, where there was 8 days at 81 degrees Fahrenheit, 8 days at 61 Fahrenheit, and 8 days at 41 Fahrenheit. And here you can see 74% is mineralizing. Now, if we look at a warming trend, like what we might expect in spring, so we go 41 to 81 degrees, 8 days at each temperature, we could see that we only have 45% nitrifying. So that's a big difference. Here we got about a 50% difference in the nitrification process, whether we're in a cooling trend or a warming trend. So this is really suggesting that in fall applications of nitrogen, why we really want to wait till soil temps are below 50 degrees to start limiting some of our nitrification, because if we're in a cooling trend and we're not quite there, we could still be nitrifying a lot. The process isn't quite as unfavorable in the spring because with that warming trend it's a little bit slower. And remember, we have to be in the nitrate form of N to lose it, and we'll get into that in a minute. So that's why it's really important to be looking at soil temperatures and knowing when nitrate is produced. So that leads us back to our nitrogen cycle. We're now here at nitrate. We can get here, as we just said, through the nitrification process, that transformation from ammonium N. Fertilizer nitrogen could also be in the nitrate form, so that's another addition. Now it's important to note that there's no arrow going from organic matter to nitrate. We need to go through this mineralization process first and then nitrification. Now once we're in the nitrate form, there's several fates. One, it can be immobilized back into soil organic matter. Secondly, it can be taken up by plants. We can lose it through denitrification, so this is where N2 gas or nitrous oxide is produced and lost to the atmosphere, or we could lose it via leaching. And so I really want to point out here, because this is a great place to do it, is that nitrate is the form of N that can be lost. We're losing it leaching or denitrification. Ammonium, we're not getting losses like that. It's really getting into the crop or back into the soil organic matter. So nitrate is the one we need to be concerned about from preventing losses. So let's focus on this denitrification loss. This is the transformation of nitrate to N2 gas or nitrous oxide. Remember, nitrous oxide is a greenhouse gas. Now, in order for this process to occur, several things are necessary. First of all, you have to have organic matter, specifically a carbon source, okay? Because the bacteria in the soil will be using the carbon, the organic matter, they'll be breaking that down. And when they get in these waterlogged conditions, because that's another condition of denitrification, you got wet soils with low oxygen, what happens there is they need an alternative electron acceptor, so then they finally move to nitrate to be that electron acceptor, if we get down to that biochemical pathway part. So carbon needs to be present. You need to have nitrate. If there's very little nitrate in the profile, you're not going to lose it through denitrification, because that reaction won't go forward, or will go forward very little. Now, the temperature where you get a lot of denitrification starts occurring probably greater than 75 degrees Fahrenheit. And pH, again, is important for these bacteria as well. And if you're over about pH of 5, that's really going to fuel where you start seeing more denitrification occurring. And I just wanted to show some data from an older study where they looked at the effect of soil temperature, the number of days where the soil was saturated, on the nitrogen loss. And what we're looking on nitrogen loss here is it's the percentage of nitrate applied that was lost. So when we have soil temperatures of 50 degrees, so relatively cooler temperatures, and we are only saturated for 3 days, only about 10% of the nitrate is lost. That's not a huge amount. But as the time of saturation increases, you can see that the amount of denitrification that's occurring increases. So here after 9 days, 73% of the nitrate that was applied has been lost. Now if we move up to 68 degrees, now again, these are soil temperatures, not air temperatures. At 3 days of saturation, we have about 42% of the nitrate lost. And if we go to 9 days, we're up to 82%. And you can see the effect of that time of saturation as being important, but also temperature. And here in particular, this last temperature where it's 86 degrees Fahrenheit, this is quite warm. Remember, this is soil temperature, so that's warm soil temps. it doesn't matter if you're 3 days or 9 days saturated, you're over 80% of that nitrate has been lost. So knowing how quickly denitrification can occur is important. Now granted, this study was done with one soil as it was reported, but it gives you an idea of what's happening. And when we think about overall nitrogen management, if you've had heavy rainfalls and water's been laying on the soil for a couple days, you need to stop and think, what's the soil temperature? Often we see wet conditions in the early spring and soil temperatures, maybe they're above 50, but maybe they're nowhere near 68 yet. And if it only saturation where you have ponded water or the soil's glistening still, maybe that's only 3 or 4 days. So maybe your losses are relatively controlled versus if you had more days or it was much warmer, say it was a late June when this heavy rainfalls and ponding of water occurred. Now, we also need to keep in mind that these transformations of fertilizer take time. And I shouldn't say fertilizer, inorganic end transformations, because it doesn't matter if they come from fertilizer or from organic matter or manure or legumes, plant residues. Here I just want to show that the fertilizer material, okay, is if we look at ammonium sulfate, and that's all ammonium form of N. So if we look at the time it takes to become ammonium, well, it doesn't take any time, it's already there. But it'll take about 1 to 2 weeks for that nitrification process to occur, so you have nitrogen in the nitrate form. Anhydrous ammonia, we can usually think of nitrate being available 3 to 8 weeks after application. With urea, we've got a couple steps that have to occur. Urea itself is not ammonium. It needs to decompose and produce ammonium, and that takes 2 to 4 days. And then once it's ammonium, it'll take a week or 2 to become nitrate. So overall, it's going to take 1 1/4, maybe 2.5 weeks for urea to become nitrate. Again, these are under ideal conditions where things are moving along. I want to just jump down here to urea ammonium nitrate. This is our most complex fertilizer material in that 50% of the N is urea, 25% is ammonium, and 25% is nitrate. So when we think about that, so 25% of the N is already nitrate. It's right here. It takes 0 weeks to get to nitrate. 25% is ammonium, so it's going to take 1 to 2 weeks before it's nitrate, and then 50% being urea, it's going to take 1 1/4 to 2.5 weeks to become nitrate. So this gives you an idea when you're thinking about potential denitrification losses to consider when was the nitrogen applied, what was the form applied, so has it had enough time to become nitrate, because remember we need to have nitrate to denitrify. And then you could start thinking about, well, what are the soil temperatures and how wet was the soil, to consider whether there's a probability of having a lot of denitrification losses or relatively small amounts. And so that brings us back to our nitrogen cycle. And the next part so we just talked about denitrification. The next part we're going to talk about are the leaching losses. And now we typically think of leaching and nitrogen occur on sandy, low organic matter soils with low water holding capacity. However, we can have nitrogen leaching on silt loam soils, and it's not uncommon to measure nitrates in tile water where a field has been tile drained, and those soils can be silt loams to silty clay loam type soil, so you can get a macropore flow with nitrate moving through that and into tile. But even if you don't have tile, we can have leaching in silt loam soils. And remember, nitrate is the leachable form. And so that brings us back to our nitrogen cycle. We're kind of complete in here, but one part we can't really leave off that we need to think about is urea volatilization. Okay, so we have our spreader here, and we have this loss of ammonia from urea. So let's talk about that a little bit more. And this ties in to some of the things we already discussed. Here we have the urea molecule. It needs to be decomposed. In order to do that, we need the urease enzyme. Okay, this enzyme is ubiquitous in soil and crop residue. So it doesn't take a lot to convert the urea so that we ultimately are producing ammonium. Now, if we have the urea is incorporated, that ammonium will bind to the soil's cation exchange capacity. However, if the urea is just sitting on the soil surface, there's not much ability for that ammonium to bind, and we will lose it. It will convert to ammonia and then be lost to the atmosphere or volatilized. So we need to control that type of loss to ensure efficacy of our fertilizer. So here's a few conditions that favor high losses, or just losses in general, I suppose, from surface applied urea. Number one is no rainfall after application. Typically, if you have no significant rain within 5 days of application, you may lose a lot of that urea. It will volatilize. Higher temperatures are much worse. High soil pH, because this last step, if we go back here one, you'll see this ammonium plus a hydroxide, okay, that's going to be occurring more at higher pH, will produce ammonia. So if we have a higher pH soils, we're going to be more likely to have volatilization losses than somewhat lower pH soils. And if you have intermediate humidity between 50 to 90%, so you need moisture. If it's hot, there'll be more issues. Soils with low clay and organic matter content, low cation exchange capacity to bind the urea are also issues. And then in particular, if there's a lot of crop residues on the surface, because if you've surface applied that urea and there's a lot of, say, corn residue, it's possible for those urea granules to get caught up in the residue, and they never actually get into the soil, but there's urease within the crop residue that's causing that urea to decompose. So there's a number of things that can be thought about. We will have bigger losses if you are surface applying urea during the growing season, either as a sort of a June application to corn, or if you've got a grass crop, like a hay crop, where you're doing a surface application in June or say August, you have much higher humidity and also typically temperature that you're going to potentially lose more. And with that, we'll just take a break for a moment, and then we'll move into our next section.